So this work is joint work with Mitani and in the project called Erato project. And so the motivation of this work is that interaction with deformable object is difficult. You know, like closing or lobes with high degree of freedom, it's very difficult. And I think there are two approaches to work on with these things. So one is to use physical simulation, you know, continuously run simulation and then take care of physics. So this is nice, but it's kind of inflexible. You cannot do something contradict to the physics. So if you want to switch, you know, this one and this one, then you cannot, you know, penetrate each other. So you need to go around, moving around, it takes time. And instead, if you use direct manipulation, standard CAD modeling, you can do whatever, you can do everything, but it's very tedious. You know, you have to take care of physics manually, which is very difficult. So, you know, these two approaches not very perfect. So what we do is somewhere between the two. You know, instead of doing perfect physics, we introduce a couple new semantic level operations. So user gives some sort of intuitive request to the computer, and then computer takes care of the rest, taking care of physics. So that's idea behind this project. And in this particular work, we introduce layer operations, usually seen in 2D graphics like PowerPoint and so on. So you just bring back or bring in front, and then these operations are usually in 2D graphics. So in this work, we introduce these layer operations for 3D modeling of layered cloths or lobes and any deformable objects. And yeah, more specifically, we introduce two operations: layer swap, and click and swap layers, and then also, you know, dragging, and then system adjust steps appropriately. And our main contribution is interaction technique, these ones, but I think there are a couple of interesting aspects with this algorithm, and I want to share it with you. So yeah, layer swap is very easy. Just click somewhere, and then system swaps the layers between the topmost layer and then one beneath the top one. So if you click here, you know, you get this result. If you click here, you will get this result. And this is completely a 3D model. And this is second technique, so layer-aware dragging. So as a user drags the object, and then user can specify whether you go under or go over by pressing shift down or shift up and so on. And let me show you a demo. So yeah, so we have a 3D model here. You know, it's completely 3D, and then physics simulation is running, so you can see, you know, typical behavior. And then if you want to swap this layer and this layer, you know, if you use physics, it's very tedious. You go back and forth and change view, you know, depth correction and so on. But here, you just click here, and then system swaps the layers, and then you will get this result. And then if you click here, you know, just click here and then swap layers. And I think this operation is very, very tedious if you use physics simulation or direct manipulation. And then you can, of course, you can do this. Oops. Hello. Yeah. And then here's a little bit complicated. You have three things. And then if you click here, if you swap green and blue, and if you just swap layers in this region, you know, there will be interpenetration somewhere here. So system takes care of these things, and then you will get this result. This result may not be directly intuitive for you, but you can, you know, easily swap additional layers by successive clicks, and then you'll get some reasonable result. And then here's more getting complicated. So we have now here a folded cloth here. And then if you click here, system tries to swap blue and purple. But if you do that, then there will be an intersection here. So that's not good. So system automatically identifies this potential interpenetration and then pushes the purple one all the way back to the bottom. So this is kind of analysis going on behind the scene. And this is a little bit more complicated one. This is a kind of folded handkerchief. And if you click here, what result do you expect? You know, if you simply swap these two layers, there will be interpenetration somewhere here. So system automatically pushes all the way back to the bottom, and then this is the result. And so yeah, so this is another example. You know, if you click here, then this is spiral. If you want to flip this one and this one, if you do that naively, there will be some interpenetration, something strange happens here. So in order to properly do this, system actually swaps all the way upside down, and then this is the result. And yeah, lots of analysis going on behind the scene actually. And then, yeah, this is my favorite one. And you can do something like completely change the orientation of this guy, and then you can do something like this. So, yeah, so this kind of operation can be very tedious in the real world, do back and forth and so on, but you can get this result. And then here is a loop example. If you have a 3D loop and then, successive clicks, then, change the direction. And yeah, again, you have 3D model here, and then you can successive clicks will, swap the direction. And yeah, you can do, this is a kind of weaved thing, and then you can click to change different. So I think this kind of operation is very, very useful experimenting with many variations of same model, which is very important for design process. And so that's the layer swap. And then now let me show you the layer where dragging. So you can drag something, and then if you do nothing, it's always go over. However, if you shift key down, and then you can go under. And then you can continuously change, like shift down, go under, shift up, and then go over, and then you can get something like this. And here is a textured model. This is again completely 3D. And then if you say shift down, and then go down, and then shift up, and then go over, and then you can get something like this. And yeah, here's a loop example again. So you grab this one. Oops. Go up and down and then up, and then you can make a note. And you can do something like this, and then, yeah. So this can be very, oh, thank you very much. So that's a demo. And so, yeah, so our work is directly inspired by local layering paper last year. So they introduced per overlap layers. So usually layers are consistent single order, but here, yellow under purple and then yellow over purple here. So this is a local layering. And we actually started this project after reading this paper. It was very interesting. And then built on top of this work, we introduced, our contributions we extended this to completely 3D modeling. So the target application is completely different. And also we support self-overlap and then folds, which are not supported in the original local layering paper. So that's our contributions. So yeah, there are a couple of other related work on origami theory, and we also worked on closing manipulation interface before, but there was no cross interaction that time. So let me introduce user interface first. So the details. So if you click here, the user request, semantics of the user request is swap layers between yellow and purple. But there are many possibilities, right? The one possibility is bring yellow to the front, or bring the purple to the back, and something else. And we actually internally quantify the number of changes, and then picks our changes with the least changes. So this result may not be intuitive, maybe at the first sight, but as I said, you can just click somewhere else to obtain the desired result. And here's I already explained this. If you click here, if you just swap yellow and purple, there will be independent iteration, so system picks the right one. And yeah, this is a complicated case, and actually in this case there are two possible solutions, and then again, your system returns the one with minimum changes. If you want to get this one, then you can additionally click somewhere here, and then you will get this one. And yeah, as again, spiral. If you click here, system actually, completely reverse the order. So that's details, and let's go into the algorithm. So this is a pipeline. So this is 3D scene, input 3D scene, and if you click somewhere, system first project everything to the screen space, and then compute a 2.5D layer structure, and then also internal relationship, like this is called list graph. Nodes represents a specific region, and then you see layers in each node. And then system operates on this 2.5D list graph structure, and then you get updated list graph. And then system synthesize and then apply physical simulation, then you get the resulting 3D scene. So that's the pipeline. And so the first part, so I will describe this process one by one. So the first process is to convert 3D scene into 2.5D list graph. So this is basically combination of previous work. So there are lot of work on vectorization. Converting 3D scene to 2.5 layer graphics is already done, and so we just do that. And then after that, we compute a list graph, analyzing the layer structure. It's the same as the previous paper. And then, so we swap layers. And this process is the main part of the algorithm. And the requirement is that user first satisfy the user request. We mean, updated list graph should have swapped layers above the clicked position. And also, it is important to avoid invalid configuration, I mean interpenetrations. And what is invalid configuration? So one type of invalid configuration is interpenetration between neighboring regions. So if here blue is above red, here red is above blue, then there will be interpenetration. So this is bad. And this is already introduced in local layering paper, but we also newly introduced type 2 violation. So this occurs at the location of fault. If there is a fault, then, light blue and blue one should be connected in the layer structure, but if we have yellow between the two, and then there is interpenetration here. So system needs to avoid these type 1 and type 2 violations. So system searches for valid combination, avoiding these invalid configurations. And yeah, I think this is the most important slide here. So original local layering paper use simple forward propagation. So just greedy search one way. But this doesn't work. Let me explain. So this is a side view. And if you want to swap layer A and B, and if you push layer A into B under B, then that's fine. And then A go under B and A under C. But somewhere here, you observe interpenetration, so you may want to go backtrack. Or you have to identify that B should be above A. But back propagation also does not work, so because of self-overlap. So this is an example of spiral. If your spiral is connected everywhere, if you want to push A down B, it's fine here. But if you return here, B goes down C, and C goes down B, and then if you just implement simple backtrack, actually we did, and then the result is the same. So that's not good. So we ended up enumerate all valid configuration beforehand, and then pick the right one. So here's the details. So it's a two-step process. For each local layer, for each region, we enumerate all permutations. So yeah, this is 3 layers, so 6 possibilities, 2 layers, 2 possibilities, and so on. And then we first remove type 2 violations first, and also, this is a user request. Please swap yellow and purple, yellow and red. And then we enumerate all valid combinations free from type 1 violation. And so the second step is basically a search program. You have many combinations for each region, many orders, and then search through. And 2 approaches. So one is exhaustive search. You enumerate all possible combinations. And this is, you can get optimal result, but can be slow. And you can also switch to beam search, narrow down the search space. And the result may not be perfectly optimal, but it's very fast. And I think we should choose appropriate one depending on target applications or target situation. But in our case, most models are simple, and then we use exhaustive search. And final process is kind of straightforward. Given the updated list graph, and then we convert it back to the 3D space. And this is done in a 2-step. So first, you get list graph, and then for each region, it represents some constraint. And then using this constraint, we solve some least squares problem, and then you get something like this. And then after that, you apply physics simulation, and then gravity pulls everything down, and you get this result. So that's the layer swap algorithm. And layer drag is much more simple. So you have a current location, and then you analyze the layer structure, green on top, red, and yellow. And then this is the target location, and then you analyze layer structure as a target location. And then before and after position, you establish correspondence. These two are connected. So now you know that red should not be go over green to prevent interpenetration, and red should not go under yellow. So these yellow and green determines the upper and lower bound, and then within this region, whether you use a shift up goes over and then shift down, drag go under, and then you see you cannot go here, but you can just go take a different path, and then you can get the result. So I already showed main result in the demonstration, so I won't go into details, but one example is tie. So this is fairly complicated layer structure underneath, and if you click here, you can quickly get this kind of result, and without changing other locations. And here's a little bit of statistics. So the number of valid combination is bigger in tie case. So spiral case, only one valid combinations. And then, this planar map construction and construction list graph dominates when the combination is filled. So this is dependent on the number of vertices. And then going to the list graph manipulation, exhaustive search is very fast, but then gets very, very slow when many overlaps. But beam search can be very quick. So this means it takes about 1 second or 2 seconds. And I think this is an upper limit if you use exhaustive search. Okay, so what's the limitations? So most reviewers complain, how often do you need this? Who use this? And I agree. And this is not the tool you do use every day. But maybe once a year you want to use this, and then this will be very, very useful. If you want to layer swap manually, it takes time. And result is, especially again, if you want to explore many variations of a knot, you can do only few variations if you use traditional approach. But by single clicks, you can try many, many variations. Result should be better. And our current implementation assumes top-down view. And and also scalability is an issue, but I think, in the real world, how many layers you use, only 2 or 3. Famous Japanese traditional kimono has up to 12 layers, but that's the most, I think. And also, in the future work, we want to explore many other physics-aware semantics operations. So to conclude, I introduced layer operations for 3D drawing, 3D modeling, so layer swap and then layer dragging. And our work builds on local layering paper, but the difference is that we apply it to complete 3D modeling, and also we support folds and self-overlap. And the algorithm is that we examine all combinations and then return the best one. So that concludes my talk. Thank you.
Thanks. We have time for maybe 1 or 2 questions.
I'm Frank Little from Joe Alder Company. It looks like you've got the perfect tool to sort out the motion paths in something like the first pass on Star Wars to get the matting order right.
So, I haven't thought about it, but you mean motion path has many layers?
Yes.
Okay, thank you. I will look into it. Thank you very much.
Hello, this is Vivek. My question is, does the determination of valid configuration need user input, or is it done automatically?
Excuse me, I'm not following.
There is a determination of valid and invalid configurations out of graph. So is it done automatically, or does it need manual input?
Oh, it's automatic. All the user need just click, and then system examines each pair is invalid or not.
Oh, thanks.
Are there plans for releasing the source code to this application?
I don't remember. I think I already did. Maybe you can just search.
Cool.
Okay.
Thank you.
Thanks again. And great scarf, by the way.